Welcome to today's presentation on predicting unexpected behavior in industrial deep bed fluidization reactors and developing engineered solutions with CFD. Before I continue, I would like to recognize the important contributions of my co-author, Dr. Ken Williams, who is the primary author of the work you're going to be seeing today. Ken is the co-founder and co-owner of CPFD Software, the makers of Barracuda Virtual Reactor, and together with his partner, Dr. Dale M. Snyder, is working to continuously improve and popularize the use of this important computational method for better understanding and optimizing the behavior of fluidized bed reactors. In today's presentation, I'm first going to briefly describe why fluidized bed reactors are important, and then state our premise very clearly, which I will then proceed to prove throughout the rest of today's presentation. I'm going to show some experimental results showing gas bypassing behaviors in deep fluidized beds, and then summarize some insights on that fluidization behavior. Then I'm going to show some comparison of CFD to experimental results to show the capacity of the computational fluid dynamics simulations to predict the behaviors that we're talking about here. I will then show 5 industrial fluidization case studies to illustrate how this same technology can be applied to full-scale industrial systems. And I'll leave some time at the end for a summary and some questions and answers. Why are fluidized bed reactors important? Fluidized bed reactors are used in a very wide range of industries, but they all have one thing in common. They ultimately impact the environment around us. Fluidized beds are used in coal and biomass gasifiers, which are devices designed to help us utilize coal in a cleaner, more efficient way. They're also used in circulating fluidized bed coal power plants. These are much larger scale power plants that are much cleaner than the typical coal power plants of the past and are able to achieve much higher thermal efficiencies. Fluidized beds are also widely used in chemical manufacturing. Whenever you need to react a solid material with one or more gases, one of the most effective ways to do it is to grind up your solid material into a fine powder, put it into a vessel, and then blow your gases through it. So these fluidized bed reactors are very often used in chemical manufacturing and for similar reasons also in fluid catalytic cracking and refining, and in photovoltaic materials production, notably in the production of solar-grade polysilicon for making solar cells. I would first like to briefly state our premise on deep bed fluidization, which I will be describing and then proving during today's presentation. To begin with, gas-solid fluidized bed reactors involve pushing a very high throughput of gas through a fine bed, typically of Geldart Group A size particles. The consequent high gas velocities will put these units into a turbulent fluidization mode, and it's thought in general that this turbulent fluidization mode provides a regime in which the gas and particles are in a desirable, well-mixed, and stable operating state. However, experimental results now challenge this assumption of good mixing and instead suggest that an unexpected behavior is often happening, an unexpected behavior called gas bypassing. It's our premise that in the turbulent fluidization regime, the gas must pass through the particle bed as narrow, high-speed jets or streamers, which form low in the bed and can penetrate its full height, often 12 to 16 feet or more. The fluidization mode within the bed can then be characterized as either a well-mixed turbulent mode in which the gas streamers randomly form, penetrate the bed, but then collapse and reform, or a gas bypassing mode in which the gas streamers remain stable, either attached to a wall or to an internal structure. To continue, some degree of gas bypassing is likely occurring in almost all deep beds. The phenomenon itself is time transient, highly 3D, and depends upon 3 primary factors: the gas velocity, bed depth, and particle size distribution. In addition, there can be multiple species of particles, each with its own PSD, subject to change while the reactor operates. To date, there's been no practical, experimentally determined method for clearly characterizing gas bypassing. when it is occurring, and to what degree. However, our position is that even absent a consensus on characterizing and fully understanding this gas bypassing phenomenon, multi-phase CFD technology has been shown to predict these streamers and their impact on fluid bed operation. This morning, I'll be showing comparisons of CFD simulations with large-scale experiments that validate this approach. In addition, I'll be showing CFD simulations for operating industrial-scale reactors that also show agreement with experimental data and/or operational experience and observations. These same industrial examples illustrate the real value of the method to help understand gas bypassing and other non-uniform flow conditions and lead ultimately to engineered solutions for optimization of reactor yields, emissions, service life, and on-stream availability. To begin with, we would posit that validation requires the use of large-scale experimental data. There is certainly some value in validating against benchtop experiments, but if you're trying to develop a technology for modeling industrial-scale units, the use of large-scale experimental data is preferred. We have obtained a wealth of experimental data through our membership in an industrial consortium in Chicago called Particulate Solid Research Incorporated, or PSRI, who have run a number of experiments in deep bed units with a variety of powder types, usually Geldart Group A. These results have been widely published, and many of you have probably met Ted Knowlton, Reddy Carey, Ray Coco, or other of the major contributors from PSRI. Here you can see a comparison with a Barracuda simulation on the left with a video of an experiment run at PSRI back in 2008. This shows that the Barracuda simulation is able to recreate the behavior in this bed with a startling degree of accuracy. You can see that the overall structure of the gas streamers, the shedding frequency, the shape, and even the cross-sectional area of the bed taken up by the streamers is very closely matched by the CPFD simulation. I should point out that this simulation you're looking at is several years old, at least 4 years old, dating back to 2008. So it's not only the experimental data, but the simulation itself, which dates back quite a ways. So we have been at this for quite a long time, trying to develop a better understanding of gas bypassing behavior and how to model it. This is another case, also based on data from PSRI, that was part of a U.S. Department of Energy 2010 challenge problem intended to provide data for validation of CFD software for multi-phase flows. In this particular study, we were able to see not only the gas streamers, as we did in that prior case, but the impact of those on those gas streamers of the three important parameters: the bed height, the superficial velocity, and the particle size distribution, or in this case defined as the fines content within the bed. The analytical results were in very good agreement with experimental data on pressure distribution in the bed. So here you can see the PSRI experimental data on pressure drop, DPDL, versus the Barracuda simulation. And you can see that they essentially overlay one another. But one of the things that we have learned about this gas bypassing behavior is that DPDL does not tell the full story. Even if you are getting the same pressure drop across the bed, you can, depending on how some of these other parameters are varied, end up with a fluidization behavior which is very different. I guess an easier way of putting this would be that pressure taps on your vessel to determine your pressure drop across the bed are insufficient for characterizing whether the bed is in a gas bypassing mode. So here we're looking at a study of the bed height. So here's a 4-foot bed on the left, 8-foot bed in the center, 12-foot bed on the far right. The very shallow bed exhibits what we would ordinarily call a good fluidization behavior. Turbulent fluidization, very limited gas bypassing, no quasi-steady or steady flow structures or streamers building up along the walls or any of the internal structures. In the center experiment, you can see that stable gas streaming is beginning to appear. So you're seeing a lot of gas being blown through the bed, which is going to create a pore fluidization characteristic elsewhere besides those streamers. Plus, you're blowing a lot of gas through the bed without providing the proper gas-solid contact, which is typically the purpose of a fluidized bed in the first place. On the far right, the situation is even worse, where you can see that the gas bypassing is constant along the walls of the bed. And there may be even more gas bypassing going on in the middle, but the experiment doesn't allow you to observe any deeper than what's happening at the walls. Based on a series of experiments that PSRI conducted in a 3-foot diameter unit, they looked at gas velocity, bed height, and fines content and their impact on the fluidization behavior. One of the findings is that ascertaining a gas bypassing mode inside a non-transparent vessel is very difficult, since the bed pressure differential remains almost unchanged regardless of the fluidization mode. PSRI data also show the dramatic impact of particle size distribution on fluidization behavior. A 4-meter deep bed operated at 0.6 meters per second was well fluidized at 12% fines. However, if you drop the fines to 4%, the bed height would need to be reduced to only 0.7 meters to remain within that same turbulent fluidization regime. Phillips Petroleum did a study back in 2001 also. They conducted similar bypassing experiments, in their case in an 8-foot diameter vessel with bed heights up to 16 feet. Their data are proprietary, but they did publish some conclusions, including that the flow regimes observed were significantly different than expected. The flow pattern was a snake, which we are now calling a streamer or gas streamer, which rapidly formed above the grid and passed through the bed. The behavior that Phillips had observed, as opposed to the PSRI experiments, showed that at the superficial velocities that they were looking at for a bubbling fluidized bed, the fluidization appeared to be independent of fines content. But it's possible that their fines content didn't drop low enough in some cases to impact the fluidization behavior dramatically, or possibly that their larger diameter bed may have had something to do with the sensitivity of fines content. But there's no questioning the impact of particle size distribution on fluidization behavior. So what are we to conclude from some of these experiments that we've looked at? What we would conclude in our premise is that at typical fluidization gas velocities above, say, 0.45 meters per second in a deep bed, turbulent fluidization requires a 3-dimensional flow regime of the gas and solids. If you try to assume a 1D or plug flow situation, all the solids will be blown out of the domain. As a result, gas streamers must form at this velocity in order to allow the gas to move through the particulate bed material. Gas streamers are highly nonlinear and unstable. Continuous, randomly forming and collapsing gas streamers gives rise to what we call a good turbulent fluidization. However, when the streamers become stable and attached to either walls or internal structures, gas bypassing can occur, resulting in poor mixing and fluidization. This results in poor gas-solid contact, reduced chemical reactions, poor yields, also high-speed impacts of particles onto structures, causing erosion, or hot spots or cold spots from the impeded mixing and heat transfer as a result of the poor fluidization in areas away from the gas streamers. Gas bypassing is very difficult to detect in an operating reactor, but the impact of gas bypassing can be predicted with existing multi-phase CFD technology, which is what we'll look at now. All of the simulations I'm going to be showing today were performed using the Barracuda Virtual Reactor or Barracuda VR software, which is based on the CPFD method, which is more generically known as multi-phase particle in cell. Now, what makes this multi-phase particle in cell uniquely capable for modeling fluidized beds? There's a number of characteristics. The first is the ability to define particle size distribution in detail for any number of solid species, and then modify that PSD as a result of chemical reactions. Second is a close coupling for the exchange of mass, momentum, and energy between the continuum gas and the discrete particulate solids, and the capacity to model fluidization regimes from dilute to dense packed at the same time and in the same domain. In addition, it's necessary to model the chemical kinetics in detail for gas-gas, gas-solid, and solid-solid chemical reactions for the simple reason that these devices are most often designed, built, and used for the purpose of operating a chemical process continuously. If we could do those first four items, but could not model anything larger than a coffee cup in a reasonable time, we wouldn't be able to have an industrial solution for real operating fluidized beds. So we also need number 5, the speed and capacity to simulate industrial scale fluidized beds with very large particle counts. Now here's a comparison between Barracuda simulations and the same PSRI experiments we were looking at before. You can easily see on the far left that the turbulent fluidization behavior is captured in the Barracuda simulation when compared to the experiment. When you look at the center, you can see here the streamers climbing up the wall and becoming semi-stable. The gas streamers are forming in the lower part of the bed and extending out through the full bed height. And you can see, of course, the same thing occurring in the experiment. When you go to the 12-foot bed height, you can see that in some cases, streamers begin to form even in the middle of the bed, not necessarily all the way at the bottom, but in both cases can make their way all the way through the full bed height. Here we're looking at centerline slices, which make this behavior even more evident. You can see on the far left that gas streamers do form. And again, this is part of our premise, that this gas bypassing behavior is occurring in all deep beds. So you're seeing the gas streamers form, but in many cases they're collapsing before they reach the top of the bed height. In the center, you can see the bubbles or gas streamers climbing the walls. And in the far right, you can see that the gas streamers are forming even in the middle of the bed and away from the walls in the 12-foot bed height. It is obvious that this gas bypassing behavior is very dynamic and unstable, and therefore a time transient calculation is required to capture it. The CFD method used must be able to capture the formation of these gas jets or streamers and also their collapse and reformation if you're in a turbulent fluidized bed mode. And if the behaviors become stable, attached perhaps to a wall or cyclone dip leg, the method must be able to capture the gas bypassing that occurs. Some experts believe that gas bypassing is always occurring in deep bed units, and it's only a matter of degree. Even if you are using a time transient method for capturing the gas streamer behavior, some time averaging can still be useful for understanding the overall bulk flow. Here we're looking at a comparison, all for the 12-foot bed, of instantaneous values on the left with time averaged values on the right. If you are looking at simply instantaneous solids volume fraction, it isn't necessarily really clear what's happening in the bed. But if you do time averaging, as we've done here, you can see in these centerline slices that there is some fairly consistent flow structure forming in this 12-foot bed. You can see on the far right, where we're looking at the average vertical velocity, that over most of the cross-section of the bed, the particles are moving downward slowly. And in the center of the bed, and in some cases along the walls, the particles are moving upward, but comparatively quickly compared with the downward particle flow in this annulus around the vessel. So what do we do with this better understanding of fluidization behavior? I'm going to show now 5 different industrial fluidization case studies. I'm going to move through these quickly, but I hope to show all 5 of you today in the time allotted to demonstrate how this software, how this method has already been used to model real industrial fluidized systems and devise engineered solutions for different problems that had occurred. The first case is a circulating fluidized bed combustor that is located in Strongoli, Italy. It is owned by Biomass Italia. When the plant was first constructed, they discovered very severe erosion in the plant, particularly in the cyclone inlet, as a result of the very abrasive biomass fuel they were using, which is a mixture of wood chips and nutshells. So the 40 megawatt unit had to be shut down after only 1 month of operation for repair of the refractory. They subsequently made some changes to the cyclone geometry and were able to stretch that operating period out to 3 months. But a more typical service interval for a plant of this sort would be 2 or 3 years, not 2 or 3 months. So Biomass Italia hired CPFD software to do an erosion study of the CFB. The interesting thing about the study was that Biomass Italia needed to minimize erosion damage throughout the plant, not only in the cyclone inlet, but also in the downstream suspension tubes and in the fluidized bed heat exchanger as well. So it was necessary to model the entire loop and optimize erosion throughout at the same time. Here is the computational model for the primary CFB loop, which includes the combustion chamber, seal pot, fluidized bed heat exchanger, cyclone dip leg, cyclone, and cyclone outlet. Here we're looking at the boundary conditions which were applied. There were a number of them: fluidized bed heat exchanger, air, there was seal pot air, primary air, secondary air, etc. It was also necessary to characterize the particles in the unit as well. There were 3 different species, all of which were modeled: sand, fly ash, and bottom ash, and a different PSD was applied for each one. Now, this was a non-reacting case, so we were not modeling the system with the combustion taking place because we were really more interested in what was happening to the particles and where they would be hitting the internal surfaces. So here is what the CAD geometry for the Biomass Italia unit looked like when we started, and this was the starting point for the CFD gridding process that began the simulation. So we're looking at some of the boundary conditions. Here are the secondary air inlets, the fluidized bed heat exchanger air, primary air, etc. Here are the downstream suspension tubes and then the pressure boundary condition applied at the exit of the domain. The unit was initialized with 70,000 kilograms of sand, and you can see here the fluidization behavior, and you can even see some of those gas streamers that we've been talking about forming through the bed and moving up the riser along the walls. Now we're going to look at different aspects of the simulation at the same time. In the center is the particle speed, and on the far right is the particle vertical velocity. So you can see here where the particles are predominantly moving up versus where the particles are predominantly moving down. And again, if you see those pink areas on the far right, those are gas streamers that are climbing the walls and pulling the particles along at high speed with them. Cyclone, of course, was modeled in detail, and you can see here the separation process of the particles through the cyclone. The high erosion area, of course, is immediately opposite the cyclone inlet, and that was a main area of study in this particular piece of work. Here we're looking at the actual erosion results from the erosion index that was calculated from the Barracuda calculation. Above, you're looking at the original design, and below, the optimized design based on the Barracuda simulations. And you can see that there is a dramatic reduction in the erosion that is predicted for the cyclone inlet. And we had similar results for the suspension tubes and for the fluidized bed heat exchanger. So in conclusion on the primary CFD loop case, the CPFD multi-phase CFD method allowed engineers to select the best trade-offs for maximizing service life and performance for the CFD. This was a full-scale commercial unit. The results of the CFD compared well with the operational data. The modifications to the plant were completed in early 2011, but the full service life extension is not yet known because the plant is still operating. This next case is a full-scale 3D reacting simulation of a commercial FCC regenerator at a California, USA refinery. The Regenerator is a very large vessel, about 21 meters tall, about 15 meters in diameter, with complex internal structures, including 12 pairs of cyclones, primary and secondary, and an unusually complicated spent catalyst distributor comprised of 17 arms, which distribute the catalyst through nozzles that perforate the arms, the catalyst entering the distributor from below. The reason for this simulation was to look for root causes for afterburn, which is a temperature increase between the top of the bed and the cyclone inlet. There were some suspect areas to look at in trying to determine what the root cause might be, including whether the long spent cat riser was delivering the catalyst to the distributor in a non-uniform way and whether that mattered, and also whether a comparatively low bed height was resulting in insufficient dense bed residence time. This is the full CAD geometry for the FCC Regenerator. We actually divided this simulation into 3 models. Model 1 was for the spent cat riser and included both the thermal and chemistry effects. You can see this nozzle at the bottom of the model on top of that bend, where the spent catalyst is coming down from the reactor. The spent cat comes down from above, and then the lift gas sweeps it up the bend, up the riser, and into the regenerator. So we used flux planes at the exit of that riser and used that as the boundary condition for the model of the distributor, which was the second of the 3 models used. Here we're modeling the regenerator with hollow distributor arms, and we're doing it to try to determine the mass flux of spent cat through the nozzles that are located on each of the distributor arms. The flux planes are used to determine that mass flux, and then that mass flux that we've determined from that model number 2 is then fed into model number 3 as boundary conditions for the fully reacting FCC regenerator simulation. So each of those red spots is the boundary condition for incoming spent catalyst. Now you're looking at a slice of the FCC regenerator, and you can see the catalyst withdrawal pipe on the right, where the regenerated catalyst is withdrawn for bringing the cat back over to the reactor and continuing the cycle. Now we're looking at the thermal and chemistry results from the simulation, which is really the core of what we were studying. Over on the far left, you're looking at the fluid temperature, then the mole fraction of oxygen, CO2, SOx, and NOx. What was discovered through the simulation is that there is a significant amount of gas bypassing going on around the perimeter of the unit. So there's an excess amount of combustion air which is bypassing the bed, leaving the center of the bed, if you notice the figure second from the left, leaving the center of the bed oxygen starved. So there's essentially less oxygen, an excess of oxygen in the center of the bed, a deficiency of oxygen in the center of the bed, and an excess of catalyst. This suggests several different ways to address the afterburn phenomenon, including either putting less cat into the center of the bed or putting more air into the center of the bed, both of which were suggested to the operator as possibilities. Here you can see in the vertical temperature profile that the CFD simulation captured the afterburn phenomenon, which has been well documented in this unit. You can see it's offset slightly to the left because of the presence of the withdrawal well. But the afterburn is about 100 degrees, and that's what the CFD simulation ended up predicting as well. Cooler temperatures were observed in the dense bed at and just above the spent catalyst distributor arms and air rings, and the highest temperatures were observed on the side opposite the withdrawal well. Here we're looking at two animations which show an overview of the coke combustion. The coke combustion kinetics strongly indicate that the combustion airflow at the outer ring dominates the regenerator performance, and again effectively leaves the bed oxygen starved in the center, which is almost certainly contributory to the afterburn. Concerning the dense bed residence time, the CFD simulations did indicate that the insufficient dense bed residence time is likely contributing to the afterburning, although it may be a secondary effect compared to the combustion air bypassing the bulk of the bed. This is an unusually shallow dense bed for a regenerator, and there is a relatively large non-fluidized zone at the base of the regenerator where the gas flow out of the distributor arms is insufficient to sweep the particles off the slanted surfaces of the reactor floor, so particles tend to build up there. Supporting evidence for this lack of dense bed residence time is high levels of oxygen exiting the dense bed and significant jetting around the perimeter. In conclusion on this case, it was clear that the CPFD multiphase CFD simulations accurately modeled both the gas particle hydrodynamics and the coke combustion chemistry, at least sufficiently to capture the afterburn phenomenon. This was a full-scale commercial unit, and results of the CFD compared well to operational data. It captured the afterburn phenomenon and suggested that bypassing of the combustion air up the walls was contributory to the afterburning. The important thing I'd like to point out is that this problem has been present in this unit for 70 years, and a lot of suggestions have been put forward as to things that might be causing it, but this CFD simulation provided a lot of additional insight which will almost certainly result in engineered solutions to mitigate, if not eliminate, the afterburning in this unit. This next case shows a simulation of a circulating fluidized bed combustion chamber of 250 megawatts located at the Duisburg, Germany municipal power plant. This simulation was intended to study the combustion kinetics for the coal-fired power plant and also explore the influence of substituting 25% biomass material for the coal that's normally burned in the plant. Barracuda was selected for its speed and accuracy in understanding CFD systems, and also because it combined the chemical reaction kinetics with an accurate model of the particle fluid flow. This is, as you can see, a very large unit, about 5 meters in diameter at the bottom, about 30 meters tall. Here are the different entry points for primary air, secondary air, for fuel, and recycle ash. There are some important geometric details in this unit, including heat exchanger modules in the top and nozzles at the bottom that feed in the combustion air. Here we're looking at a plot of particle velocities in the unit when coal-fired. It showed near wall downward velocity of about 2 meters per second with upward velocities in the center of the bed. Now we're looking at the coal particle kinematics and temperature. Here we're including the homogeneous oxidation of coal volatiles in subsequent equilibrium reactions, and the heterogeneous combustion of fixed char calculated for each fuel particle. This simulation indicates that there's a maldistribution of injected fuel. In the previous case on the FCC Regenerator, it was the combustion air that was being maldistributed. In this case, because there's fuel being fed from only one side of the unit, it's the fuel feed that's maldistributed. And no matter how high the velocity of that fuel injection, it was determined that it doesn't penetrate the bed very far, and you end up with an asymmetry in the combustion as a result. When we look at oxygen distribution, both near wall and on the center plane, we can see that one side exhibits an oxygen deficit with corrosion critical values near the heat exchanger modules. There's a very low penetration depth of secondary airflow due to high solids momentum. One of the suggestions made by AX Process for the plant was to include additional secondary air nozzles higher up in the unit. The recommendation for optimizing combustion was to add these nozzles to help overcome the oxygen maldistribution as a result of the one-sided fuel feed. Here we're looking at the as-built case versus the optimized case. Of course, the fuel feed is still offset, so the fuel will not be distributed evenly, but the additional secondary air ensures that there is some offset to this maldistribution of feed, so you do end up with higher temperatures of the fuel in the optimized case because there's still oxygen feeding it in the upper regions of the combustor. So in terms of conclusions, this study showed that multi-phase CFD simulations could provide deep insight into the gas and particle kinematics coupled with the homogeneous and heterogeneous coal chemistry. The as-built case showed a maldistribution of solid fuels and volatiles, a maldistribution which actually became worse when biomass fuel was fed in at 25%. The volatiles and char burnout is limited by a local lack of oxygen. The lateral temperature gradient and corrosion-relevant oxygen deficiency at the lower end of the heat exchanger modules did match the plant operational experience. The process of optimizing with the secondary air nozzles does lead to a moderate improvement in oxygen distribution, but the plant subsequently decided that the improvement wasn't sufficient to justify major modifications to the plant. So no changes have yet been made to the plant, so the results are not yet fully known for any redesign effort. Our fourth case today is a study of a warm syngas cleanup system, Sorbent Regenerator. This is a sorbent-based process for scrubbing sulfur out of a syngas stream generated by a gasifier. simulations were performed for the Sorbent Regenerator riser and mixing zone. Over on the far left, you're seeing the full height of the regenerator and mixing zone riser, and then a zoom in of just the lower mixing zone. The goals were to optimize the design and operational parameters for the regenerator, including the location and orientation of the solid inlets, and especially the recycle ratio for regenerated sorbent. The sorbent particles entered from two different streams and have different sulfur loadings and temperatures. The requirements for being able to model this case is that you would need to have a CFD methodology that was capable of modeling dense to dilute solids loadings, and also to capture discrete sorbent particulates, each with its own diameter, sulfur load, and temperature, and track how those change as the reactions occur. What you're going to be looking at in the animation on the next slide is several views at once. On the far left of each is the full 3D geometry, then the mixing zone, then thin slices through first the west and then the north planes of the unit, because the nozzles are offset, and in order to capture them both, we need to do two cut planes. And here we see the fully reacting simulation of the sorbent system regenerator. On the left is the solids loading, then the solid residence time, solids temperature, and gas temperature. In conclusion on the warm syngas cleanup system regenerator case, this was a multi-phase CFD model that was built to model this sorbent regenerator, mixing zone, and riser with the full exothermic chemistry and energy balance. Cases were studied with spent sorbent and sorbent recycle injection points at two different locations, lower and higher. Originally, it was thought to inject the recycle at the lower injection point. However, this resulted in additional hotspots and affected the stability of the sorbent regeneration. The CFD results pointed to more likely better performance with the spent sorbent, which has higher sulfur and lower temperature, at the lower injection point. This reduced hotspots and resulted in a more stable sorbent regeneration. I should point out that this process is still being developed, but it underwent very substantial review and redesign after the results of the CFD. The last case I'm going to show you is an erosion reduction study on an FCC reactor cyclone system. The Marathon Petroleum Catlettsburg refining facility was going through a revamp, and the equipment licensor had suggested a couple of alternative designs to address erosion in the reactor cyclones and crossover ducts. It was decided by Marathon Petroleum to have some CFD done of the system to determine which of the two designs was more desirable for reducing the erosion in the unit. This is the gas boundary conditions shown for the CFD simulation at the cyclone outlet, dip leg, the bottom of the model, and then the inlets to the other 9 cyclones. There are 10 total cyclones. 1 was modeled in detail, and 9 were simulated with a pressure boundary condition. The particle properties, of course, needed to be modeled, so there was a particle size distribution provided by the operator. Here we're looking at the baseline particle flow results. You can see the residence time distribution on the left, then particle speed, and then particles colored by the disengager arm inlet, either inlet 1, 2, or 3. One of the things that you can observe is that the solids flow field has very significant transient fluctuations. The high loading through the individual cyclones tends to fluctuate. So at one moment, a cyclone might be highly loaded, and the next it might be unloaded, and the one next to it might be highly loaded. This is certainly something you can see in more detail here. As you can see, the different cyclone arms tend to fill up with particles at different times. There were two alternatives studied in this particular instance, and it was determined that the flow characteristics were noticeably different between the two alternatives and the baseline. The two alternatives looked very similar to one another, probably due to the flow straighteners that were added, and both exhibited lower velocities into the cyclone inlets. When we look at the erosion index calculations for the unit, we determine them based on some function of the angle of impact, some power on the mass of the particles, and some power, typically around 3 or 3.5, on the velocity of the particles. Using this erosion index, we were able to show the relative reduction in likely erosion from the baseline to the two alternatives. And even though alternative 2 does look to be the lowest case, both alternative 1 and alternative 2 were so much lower compared to the baseline that either one of them, it was determined, would be equally effective at dramatically reducing the erosion damage that had been noticed in the plant. So in conclusion on this case, the CPFD method was used to compute the multi-phase 3D transient flows within the outlet riser and cyclones and compute a resulting erosion index. The particle streams tend to be directed toward the cyclone centers, which is undesirable because this could lead to poor cyclone efficiency and high fines loss. So some changes to the licenser's proprietary primary separator design were suggested. There are significant fluctuations present in the solids flow into the cyclones, and both designs are expected to reduce the cyclone inlet erosion significantly compared to the existing design. Both alternative designs are expected to work, although alternative 2 could perhaps perform slightly better than alternative 1. In conclusion, unexpected, or at the very least difficult to predict behaviors such as gas bypassing, hot or cold spots, erosion, etc., routinely do occur and in many cases must occur in industrial deep bed units. These behaviors have a substantial impact on unit performance, yields, emissions, service life, and on-stream availability. Even absent a full understanding of the causal factors behind complex phenomena like these, it's clear that the comparison of the CFD results to experiments and also the cited industrial CFD examples show that multi-phase CFD technology is already available that can predict these fluidization behaviors with sufficient fidelity to make essential engineering decisions regarding operation and design of fluidized bed systems. The result of using CFD technology in this way is that designers and operators of fluidization equipment can now put real science behind critical decisions that can and do have profound impacts on the safe, reliable, and profitable operation of all manner of fluidized systems. Thank you for your time and attention.